Okay, so there's a couple more things that I feel like I should mention before we move on to the optimization of deep learning. So this is a bit of an addendum to part one. So the first thing I'd like to mention is that there's another common activation function that we like to use in modern neural net architectures, and this is the rectified linear unit. So let's edit this. So for the rectified linear unit, and we call this just ReLU for short. The basic idea is that the sigmoid of x is just going to be, or sorry, usually I've been denoting this z, is just the positive part of z. Where just remember this is z if it's positive and 0 otherwise. Right. And so there's a couple of things about this. Of course, it just looks like this, where this is 0. It's not it doesn't have continuous derivative, but it is convex and it does have a subgradient. So we'll just typically think of its gradient as its subgradient, where we just set the subgradient to 0 at 0. Right? So it's just 1. Its subgradient is just 1 when z is positive and it's 0 otherwise. Right? So this is a common one, and we often just denote this as ReLU of z. So let's just write it as ReLU of z. So this is the first thing, is that this has become a very common activation function, is to use the ReLU. And quite often you won't see significant differences in performance between the ReLU and the sigmoid function, but sometimes you do see some differences in their performances. So that's one thing I'd like to mention. And of course, in modern neural nets, we don't just take one hidden layer. Oftentimes we'll take many more hidden layers. So let's think about our computation graph for a deeper neural net. So we have our input x, and this feeds in to our first set of hidden units, which would be sigmoid of this W transpose x plus W naught. And let's actually superscript this with W1 transpose x plus W sup 1 naught. Right? And then, of course, we have W1 and W1 naught feeding into this. And these are trainable variables down here. And then, instead of feeding this into a linear output, we're going to send this in the forward step to just another sigmoid function, or to another activation function. So of course this doesn't have to be the sigmoid, this could be ReLU or whatever other activation function we're using. So similarly here we would have W2 transpose dot, so put a dot here for x, transpose dot plus W2 0. So this is the next operation that it undergoes, and it has more trainable variables for this operation. And typically we say that the combination of the variables and the operation itself, that constitutes a layer, right? So this is layer 1. This is layer 2. And so on. And you can just continue this until you're satisfied that you've undergone enough nonlinear transformations, and then you feed it to, say, a linear output. So that's another thing that it's a way of creating our decision function. And of course, just like with the linear classifiers, for example, you wouldn't just stop with that linear output. So for example, with binary classification or multi-class classification, you might have a linear function that produces your decision boundary, which is your logits. But then to go from logits to a loss function, you have to apply a softmax operation, and then also you have to create your losses themselves by using, say, the categorical cross entropy. So that, just bear that in mind. We're only talking about modifying what was linear, and then there's still the remainder of the computation graph. So that's something to keep in mind. Another thing I'd like to mention is this is what a deep neural net looks like. Neural net, and by deep we just mean there are multiple layers. Another thing to mention is that this is not the only type of layer. You could have other types of operations included here, including fixed operations, which do not have trainable variables. So, for example, pooling layers in convolutional neural nets, that's a common fixed layer, and then convolution layers is another common type of unit. Typically, with these, we call them fully connected units, or fully connected layers. Sorry, fully connected layers. Because every possible interaction between the input x and the hidden units is considered, so it's fully connected. And so, if you look up here, it becomes obvious what we mean by fully connected. We have every single possible connection between the input and the hidden unit is considered. Okay, so that's another thing to note. And finally, I'd like to talk a little bit about what you can represent using neural nets. So one thing that we considered was a high-dimensional embedding that allowed you to learn the XOR function. Now that high-dimensional embedding was strategically chosen to be able to represent the XOR function, right? But with neural nets, the basic idea is that you don't have to guess at your high-dimensional embedding. A small class of high-dimensional embeddings, a small class of neural net architectures, is going to allow you to represent a very large class of functions. And just another sort of note about nomenclature, the selection of, for example, what layers and their sizes to put where, that's what we call an architecture of a neural net. So if we choose, say, 2 layers, and then we choose, for example, ReLU activations for both layers, and we choose 10 hidden units for both layers, and then linear output, that would be the architecture. The architecture is the specification of those tuning parameters, such as the width of the number of hidden units and the activation functions. So we typically call that the architecture. Okay, and so let's talk about representing XOR. So XOR, remember, the data looks like the following. It doesn't have any label noise, so it's sort of an interesting data set. One here. And the data set looks like it has 1s here, and it has 0s here. Right? Then what we're going to do is we're going to choose a simple architecture which just has x1, x2, and 1 as its inputs. And then we're going to apply some weight matrix, W, which is going to be a 3 by 2 weight matrix. And then it's going to construct two hidden units, right, as its output, which are then going to be multiplied by some beta to produce a linear output. Right? And so, so how can we think about this? So, and what we want is to select a W to show that there exists such a W, such that this thing, such that when we apply this W and this beta, and also select a beta, such that this linear output we can create a linear hyperplane. This linear output can separate the ones from the zeros. Okay, so so first of all, I'm just going to tell you what the W is. W transpose X. We're going to make W such that W transpose X is 1, 1, 1, 1, 0, minus 1. Right? And then when we apply this to x1, x2, and 1, what this is going to do is it's going to give us x1 plus x2 and x1 plus x2 minus 1. Now, why did I construct W in this way? Well, x1 plus x2, that is going to be 2 if and is true, and x1 plus x2 minus 1 is going to be non-negative if OR is true, right? And so we can sort of find some linear combination of these two after we apply our ReLU, right? So we can create and we can create OR. Actually, another way to think about this is that the positive part of x1 plus x2 is OR, and the positive part of x1 plus x2 minus 1 is AND. That's another way we can think about this. So let's apply the ReLU. So H1 is going to be x1 plus x2, positive part of this, right? And H2 is going to be x1 plus x2 minus 1, positive part. Right? So the positive part of x1 plus x2, let's just think about what that is. That's just 1. Yeah, let's look up here at the data. So x1 plus x2, its positive part, it's 1 if x1 or x2 is equal to 1. Right, and it's 0 if neither are 1. So that it's if x1 is equal to x2 is equal to 0. So we can sort of think of it as an AND or an OR gate, right? And then x1 plus x2, sorry, the positive part, and then it's also 2 if x1 and x2. So it's equal to XOR. Sorry about that. Right. And then this one is just equal to 1 if x1 and x2 is equal to 1 and 0 otherwise. So, so that's our hidden units. So let's think about this data. If we look at if we look in the H1, H2 space, well, H2 is going to be 1 only when AND is true. And so we have, and then H1, when AND is true, when both are 1, is going to be 2. So there's a 0 here if we look at the data, if we look at the label in this H1, H2 space. And then for 1 here, we have H2 when we have H1 is equal to 1 when XOR is true, right? And H2 is 0 in that case. Right? And so we have a 1 down here. We have both XORs are down here, and then we have a 0 here. And we see that now we're going to be linearly separable in this H1, H2 space. Because we're going to be applying a linear operation to H1, H2, we can then create a decision function which is going to allow us to separate these two out. So for example, let beta be equal to 1 minus 2, then our beta transpose H is equal to x1 plus x2, positive part, minus 2, x1 plus x2 minus 1, positive part. And then when we apply this, we're going to get this. Of course, this is h1 minus 2h2, h1 minus 2h2. So now this is just a single number. When h1 is 1 and h2 is 0, this is going to produce something that's 1, 1. So this is the output, F, is here. And then we get the labels for the data is a 1 in that case. When h1 is 2 and h2 is 1, then we get, this is a 0 here. And then when both are 0, it's 0 as well. So we're going to get that all of our data, after we pass it through this neural net, is going to give us either a 1 or a 0, which matches exactly the label, right? Because this number is matching this number in this case, in both of these cases. Okay. So that's how a neural net can learn XOR, and it's a very simple neural net where you just have two hidden units. You use the ReLU activation function. You have fully connected layers, and you don't even need to include an intercept in this last layer. Okay, so so now that we've verified that this neural net can learn XOR, let's talk about various issues for optimizing deep neural nets.